Hello everyone, this is Ahmed Khalifa, and today I'm presenting our paper, Procedural Content Generation via Reinforcement Learning. In this paper, we use reinforcement learning to train level designer agent that is able to create different levels for a certain game. So instead of using search-based algorithm or constructive algorithm to generate levels directly, we could use reinforcement learning to train the level generator itself, and then use this level generator later to generate as much level as we want. So for people who doesn't know, a level designer agent or a level generator in this work is an agent that get an input as a state. This state is usually the game level, and then it returns an action. This action should be improving that level toward a certain goal that the agent is trained on. And it continues doing that until it satisfies that goal. When I started working on that paper, there was not a lot of research done in that field. Most of the work you could find is about generating levels directly for a certain game or even for general games. But there was not a lot of work to how to train like a level generator or how to generate a level generator itself. So it's pretty exciting and I wanted to explore that field. Also, reinforcement learning doesn't use a lot of data. It doesn't need data at all. You could just have an environment and a reward function and it will learn from it how to work. So it's a good idea because if you are working on a new game, the chance that you have training data or training levels or levels itself is not very highly because you're starting working on the game. And having a framework that can work directly with your game without asking you a lot about it is very good. The last thing is, after you train an agent using reinforcement learning and it takes a long time to train, you could use this agent directly to generate levels for the game as much as you want, and they usually won't take very long time to generate these levels. So you could directly, after you train, take this agent, put it in your game, and it will work out of the box. In this work, we're gonna try to find level generators for 3 different types of problems. The first one is the binary problem. So what we're trying to do is to find the level generators that can generate different 2-dimensional mazes from solid and empty tiles, such that all the empty tiles are connected and there is like a couple of unwinding passes in it, and this length is pretty long. The second one, we call it Zelda. For people who doesn't know, it's just a game where you have a player that tries to grab a key and go to the door while avoiding some enemies on the way. So to have a good level generator, we need to make sure that the generator generates levels that have 1 key, 1 door, 1 player, and the enemies are not too close to the player so it doesn't die as soon as the game starts. And also they are not simple levels, so you don't start with the player and key and door beside each other. We want them to be interesting. So the solution length of these levels has to be greater than a certain value. The last one is called Sokopan. Sokopan is this Japanese puzzle game where you have a player that tries to push crates to a certain target. So our problem is to find a level generator that can generate levels that have 1 player, have number of crates equal number of target, and the level is playable, and the solution has to be greater than a certain value. Because we're not interested in levels where the solution is just 1 step, where there is a crate and a target beside each other, and just like we need to walk 1 step and to win. In this work, we're using also neural network as our level generators that we are training. And the reason is neural networks are great functional approximator. The field is booming with tons of advancement. You can see deep reinforcement learning being used to beat the world champion in Go, used also to get very good scores in Atari games, and also to play Dota with human players. So now it's the core of our paper, which is how we're gonna do that. The first thing is the representation. So how the agent is seeing the whole system. So the agent usually will get an input, which is a certain state, and will generate an output, which is an action. So what is exactly the input and the output? The simplest thing, the input is the current level right now, and the output is which tile it needs to change and what is the value it needs to change it to. This representation is called the wild representation. The problem with that representation is if the level is too big, then you can't, it could be very hard for the agent to learn because the action space might be too big to do that. So we start thinking what we can do, and we figured that we could use something called the narrow representation. In the narrow representation, the input to the model is not only the level, but also a location. And then the model needs to learn what does it do with that location. Do it need to modify it? And if yes, what should it modify it to? Or should it ignore it? It's a smaller space. It doesn't care about the level size, but it have a big problem. The agent now doesn't have any control where exactly it's going to place the new tile. So in order to make a level, it might need to wait for a couple of steps until it reaches the location it wants and then modify it later. So we wanted something in between the narrow and the wide, so we decided to use something we call it the turtle representation. The turtle representation input is the same as the narrow. So you have a level and you have a location. But now your model can modify that location directly, as happened in the narrow, but at the same time, it could just say, no, I don't like that location. Maybe get me a location above that, or down, or left, or right. So it can move around as it's like this tiny turtle from the Logo programming language and just go around modifying the level and doing changes. Second thing is, when you're training these networks, during training, each episode in training, should we just let them modify the level as much as they want until they find a solution, or what? So the first thing is like, oh, why not? Just let it just change the whole map. But when we did that, we find that it turned terribly, because we don't learn a level generator anymore. They just train to find the most optimal level, and they collapse one single level. And whenever you give it any input, it will override it and generate this optimal level every single time. So it's not a level generator anymore, and we can't use that. So in order to solve that problem, we introduce a new hyperparameter. We call it the change percentage. The change percentage kind of penalizes the agents by terminating early if the agent did too many changes during training on that map. So if the agent just starts modifying, and there's the amount of change it did greater than the change percentage, then you just tell it, no, stop doing that, don't use more stuff because this might not be good. So that takes us to the experimental results. So we trained our models using the proximal policy optimization from stable baseline. Most of our models are very simple models, similar to the Atari deep QN networks, consists of 3 conv layers followed by 2 fully connected. We will train them on the 3 games with the 3 different representation. We also, on each of them, we trained 3 different models for 100 million frames and fixed the change percentage to 20%. And we trained just 3 different models to check for stability. Then, after we trained them, we sampled 40 levels from each of these models with no restriction on change percentage because it's inference time. It doesn't matter. What you can see in front of your table is the percentage out of all the sampled levels that reach the success for that problem. So in binary, we wanted to have a fully connected maze, and at the same time, it's very long path length. So we can see that all our models kind of reach 100% to solve the problems, and which is pretty exciting, but it was very also predicted because it's a simple problem. The second one, which is Zelda, when we tried to train all of them, we noticed that the narrow didn't perform as good as the turtle and the wide, and we think that because it doesn't have a lot of control, that might be the main reason for its low performance. And lastly, on Socopan, it's all the 3 of them, all the models on different representation perform really badly. None of them reached our success criteria. So we didn't know at the beginning if the problem is that all the generated sample levels are not playable, or they are playable but they are not hard enough. So the solution length is less than a certain value which we specified to be 18. So in inference, we decided to regenerate these levels, but now we terminate as soon as we find a playable level. When we did that, we find that 95% in the narrow are playable, 87.5 is playable in turtle, and wide also 73, which is a lot higher than what we had at the beginning. And when we looked at the level solution, it's just shorter. It's not 18, it's around 10. That was the average. Just percentage of it was above 18, and then the rest are less than that. We think it's just because it's like just a harder game. Now it's more puzzle. You need to understand more stuff about it. It's not only about navigation. It's about how to solve the game. So we think maybe bigger networks, different learning methods, or maybe training it for longer time could benefit to increase the success percentage of Sokoban to reach higher than that. This is just an image and the visualizations that show all these agents in action. And as you can see, they are pretty mesmerizing. Just watch, and I usually like just watch them. You can see that the narrow just like go line by line, modifying whenever it gets a chance to do something. On Turtle, it just move around like this tiny digger, just digging around the walls and go around and modifying other stuff. And Wide, it just like modify pretty fast, like before you see it finishes and get the least amount of changes because they have access to every single time. So in conclusion, our idea about using reinforcement learning to train level generator was a good idea. It worked on 2 of the problem pretty well. The third one might need a little bit longer training, different training method, or maybe bigger models. This change percentage idea was very effective in general. It prevented all the level generator to collapse to one single level, and it allowed them to generate a variety of different levels. You can look at these levels in the paper or in the GitHub repo. And it will be interesting to try to explore finding general goals, such as using intrinsic motivation or curiosity metrics. Another thing is, as we saw from the animations, the inference time is very small, and also it does small amount of changes, which fits pretty well with mixture-native tools, because you don't want to overwhelm the player with a lot of changes, and at the same time, your model has to be responsive and very fast. And thank you.